Hello everyone, my name is SN Patil. In this video lecture, we will discuss Fourier cosine and Fourier sine transform. The question is find the Fourier cosine transform of the function f1x is equal to 1 upon 1 plus x square, and taking help of this, we find Fourier sine transform of the function x upon 1 plus x square. So first we write the given function f1 is equal to 1 upon 1 plus x square, and the second function is f2 is equal to x upon 1 plus x square. By definition of Fourier cosine and sine, the formula of Fourier cosine is capital F of lambda suffix c for cosine. Its formula is 0 to infinity f1 x cos lambda x dx. Substitute the value of f1 is 1 upon 1 plus x square. Similarly, Fourier sine transform, the integration 0 to infinity. For sine, we consider f2, that is f2 sine lambda x dx. Okay, substitute the value of f2, that is integration 0 to infinity x upon 1 plus x square sine lambda x dx. Okay, the equation 1 is Fourier cosine of 1 upon 1 plus x square. Equation 2 is Fourier sine of x upon 1 plus x square. Okay, so here in order to solve this equation 1, the integral is of the type u upon v, so it is difficult. And see, there is a one more thing is there. In under integral, there is a two variable function is there. One is x is function, that is integration with respect to x, and the second one is lambda is function. See, the left hand side is lambda. Okay, so here we use DUIS rule. DUIS rule means what? Differential under integral sign rule. DUIS rule here. Okay, and also here the limit is constant, that is DUIS rule number 1, and otherwise it is also called as Leibniz rule number 1 for constant limit of the integration. Okay, so what is rule? If the integral is a function of the constant, suppose alpha, okay, and integration a to b, where a and b both are the constant, and inside there is a function of two variable x and alpha, and the integration with respect to x, then we apply the DUIS rule, means we differentiate this term, that is derivative of I with respect to alpha. Okay, and here d by d alpha, and when it come inside the integration, it become partial derivative, that is partial derivative of the function with respect to alpha. So this is the DUIS rule. Okay, now first we solve the Fourier cosine transform. First we consider the equation 1. Equation 1, the left hand side, that is the function of lambda, that is capital F of lambda suffix c. So instead of that, we consider I, and which is function of lambda is equal to 0 to infinity 1 upon 1 plus x square into cos of lambda x with respect to x integration. Say equation number 3. Now apply the DUIS rule. By differentiation under integral sign rule, we differentiate with respect to lambda, that is equation 3 is derivative of I with respect to lambda is equal to, here d by d lambda outside the integral, and when it come inside the integral, then it become partial, that is partial derivative with respect to lambda, okay, 1 upon 1 plus x square cos of lambda x with respect to x integration, okay, is equal to 0 to infinity. So here this is the partial derivative with respect to lambda. Other than lambda, we treated other term as a constant, that is x is constant here. So only derivative of the cosine function, and we know the derivative of cosine function is minus time sine function, again derivative of this function means derivative of lambda x with respect to lambda is x divided by constant term 1 plus x square, constant term for lambda, and then integration with respect to x. Okay, now here again it is a difficult term. So for that we adjust x, we multiply and divide here xx. We try to adjust this denominator in numerator so that it become simple for solving this integration. So we multiply and divide x here. So what we get here, 0 to infinity minus x into x square. We multiply and divide x here into sine lambda x divided by x into 1 plus x square with respect to x integration. Okay. Now here for adjusting 1 plus x square in numerator, we add 1 and subtract 1. That is di by d alpha is equal to di by d lambda, sorry, is equal to 0 to infinity minus we adjust 1, so we subtract the 1, okay, and divide by x 1 plus x square into sine function sine lambda x with respect to x, okay, is equal to integration 0 to infinity. Now separate the denominator, means 1 plus x square divided by the x into 1 plus x square. 1 plus x square is cancel and separate here. Here the minus sign is there. First we write the plus term, minus sign is multiplied to the minus 1, it become minus minus plus, that is 1 upon x plus in bracket 1 plus x square. Okay, and here we, when we separate the first term, 1 plus x square divided by the denominator, then 1 plus x square is cancelled and this minus sign, minus 1 upon x sine lambda x with respect to x integration. Now sine lambda multiplied by sine lambda x is here, that is and apply the linearity property of integration, means integration of first term, integration of second term. It can be written as 0 to infinity sine lambda x divided by x 1 plus x square with respect to x integration minus 0 to infinity sine lambda x divided by x with respect to x integration. Okay, now see the second term. In the second term, for second term, there is a standard result. We know the result is integration 0 to infinity sine of a theta divided by theta with respect to theta integration is pi by 2, where a is positive. Okay, now here the lambda is positive here. Okay, so the second integral is pi by 2. Okay, so what is remaining term here, di by d lambda. Okay, otherwise instead of that we can write I dash lambda is equal to 0 to infinity sine lambda x divided by x 1 plus x square with respect to x integration minus pi by 2. Okay, say equation number 4. Now see here in equation 4, if we again apply the DUIS rule, the derivative of sine function is cosine and the derivative of lambda x is x, x will cancel, we get the equation 3 as it is. So for that, for our simplicity, we differentiate again, differentiate equation 4 with respect to lambda. Okay, then it becomes second order derivative I lambda is equal to 0 to infinity. So we differentiate with respect to lambda sine lambda x divided by x 1 plus x square with respect to x integration. Okay, and the derivative of this constant is 0. That is second order derivative, sorry, I double dash lambda is equal to 0 to infinity. The partial derivative with respect to lambda, where 1 upon x in bracket 1 plus x square is constant, only a derivative of sine is cos lambda x. The derivative of lambda x is x divided by x 1 plus x square with respect to x. Now here x cancel, we get I double dash means second order derivative is equal to 0 to infinity x cancel, uh, cos of lambda x divided by 1 plus x square dx. Now see the from equation 3. Equation 3, here cos lambda x upon 1 plus x square is I lambda. It can be written as I lambda. Now see the new equation, it can be written as I double dash lambda minus I lambda is equal to 0. It is second order ordinary derivative, otherwise second order linear differential equation with constant coefficient. For solving this integration, see, we make the substitution, that is, see, it can be written as suppose this is equation number 5. It can be written as second order derivative of I with respect to lambda minus I. I is function of lambda is equal to 0. So here we put capital D. D means derivative, d by d lambda. So here it become a term as a d square minus 1 and I is common is equal to 0, and the solution of this kind of equation is complementary plus particular, where particular integral is 0 because right hand side is 0. So we only find the complementary function. That is, for complementary function, the auxiliary equation is d square minus 1 is equal to 0. That is, d is equal to plus minus 1. That is the complementary function c1 e to the power here the root, okay, root alpha and beta, that is e to the power alpha is 1, okay, and it is a function of lambda, that is e to the power lambda plus c2 second root e to the power minus lambda, and the particular integral is 0 because right hand side is 0. Then the solution is I of lambda is equal to CF plus PI, means complementary function plus particular integral, that is C1 e raised to lambda plus C2 e raised to minus lambda. Okay, that is the solution of the problem. Say equation number 6. Okay, so here there are two constant involved. It require, for finding the constant, it require the two equation. Okay, so we have the first equation, that is equation number 6. Okay, so for finding c1 and c2 we want the two equation, then we can find, then it become a consistent, otherwise there will be an inconsistency. Then we differentiate again with respect to lambda, that is I dash lambda is equal to c1, the derivative of e raised to lambda is e raised to lambda, and the derivative of e raised to minus lambda is e raised to minus lambda, and the derivative of minus lambda is minus. Say equation number 7. Okay, now for finding the c1 and c2, we take the help of I lambda and I dash lambda in previous step. See, this is the I lambda, equation 3. Okay. And I dash lambda, equation 4. Okay. So here we put lambda equal to 0. Put lambda is equal to 0 in equation 3, 4, 6, and 7. So first we simplify the 3. Equation 3, I of lambda is 0. See, equation 3, put lambda equal to 0. Cosine 0 is 1. Okay. That is I of 0 is equal to 0 to infinity 1 upon 1 plus x square dx. Now there is a standard formula of integration 1 upon 1 plus x square is tan inverse x, and limit 0 to infinity. Put upper limit, tan inverse infinity is pi by 2 and tan inverse 0 is 0. Okay, so we get I of 0 is equal to pi by 2. Okay, similarly put lambda equal to 0. Suppose this is equation number 8. Similarly put lambda equal to 0 in equation 6. Equation 6 is I of 0 is equal to, so here simply e raised to 0 is 1, that is c1 plus c2. Say equation number 9. Okay, now put lambda is equal to 0. Now next, in equation 4 we substitute here because I dash, now we discuss the I dash. When we substitute lambda equal to 0, sine 0 is 0. So here minus pi by 2 is remaining, that is equation 4 I dash 0 is equal to minus pi by 2, and same value substitute in 7. Equation 7 I dash 0 is equal to c1 e raised to 0 is 1 minus c2 e raised to 0 is 1. Okay, now this is equation 10 and this is equation 11. Now see, 8 and 9, left hand side is same. From equation 8 and 9, left hand side is same, so that right hand side is same. Similarly 10 and 11. Okay, so we get here c1 plus c2 is equal to pi by 2. Okay, and from 10 and 11, left hand side is same, right hand side is also same. c1 minus c2 is equal to minus pi by 2. Now solve this simultaneously. Here c2 is cancelled. Pi by 2 minus pi by 2 0, that is 2 times c1 is equal to 0. So here we get c1 is equal to 0. Substitute c1 equal to 0 here. Substitute c1 equal to 0 in first or second equation. So we get c2 is equal to pi by 2. Put c1 and c2 in equation 6. Put in equation 6. So we get equation 6 is I of lambda is equal to c1 is 0, c2 is remaining, c2 is pi by 2 e raised to minus lambda. Okay, now see the equation 3. The equation 3 is cosine transform. I of lambda is cosine transform, that is 0 to infinity 1 upon 1 plus x square. Okay, cos of lambda x dx is equal to pi by 2 e raised to minus lambda. Okay, that is first answer. Okay, this is nothing but the f of lambda suffix c. Say equation number 12. Okay, now here for second question we differentiate this with respect to lambda. Then what happened? Differentiate equation 12 with respect to lambda, then 0 to infinity. Okay, the derivative of cosine function with respect to lambda is minus sine lambda x. Again derivative of lambda x is x. Okay, with respect to lambda. Okay, 1 plus x square with respect to x integration pi by 2. The derivative of e raised to minus lambda is e raised to minus lambda, and minus the derivative of minus lambda is minus 1. Both side minus sign is cancelled, so we get what? 0 to infinity x upon, this is x, 1 plus x square sine lambda x is equal to, with respect to x integration, is equal to pi by 2 e raised to minus lambda. Okay, so this is the second solution. So this is what Fourier sine transform of x upon 1 plus x square is pi by 2 e raised to minus lambda. Okay, thank you. Thanks for watching.